My name is Gabriel. I'm a mechatronics engineer at the Controls Integration Group from the beamline engineering division from Sirius, the Brazilian synchrotron light source. And I'm presenting here a platform for a framework for developing digital controllers for our high-performance mechatronic systems at the beamlines. To be more a collection of techniques, control theory we are using, not so advanced control theories as my colleagues, but I hope it's interesting. And so the Sirius is a fourth generation synchrotron light source. It's located in the Brazilian Research Center for Energy and Materials. It's our second synchrotron light source. The first one was UVX, decommissioned a few years ago. It was a second generation. And as a fourth generation light source, it provides a much better beam. So it's a smaller beam with a higher flux, which allows experiments in smaller scales and faster processes. So we need not only to provide a better beam, but also better beamline components. So we needed to improve the techniques we use it to exploit all the possibilities that a fourth generation light source would enable. So we need to try to come up with high performance mechatronics. And this is a body of knowledge that has been constructed since, I don't know, maybe almost 10 years, for almost 10 years, by the community and along with some partners. So we have partnered with my partners. They are here in this event as well. And this is a very multidisciplinary task. So it involves mechanical, electronics, thermal, and also control. And I'm here presenting only the control part. So we came up with a kind of workflow for designing the controllers. So it starts already in the mechatronic design itself. It takes already in consideration to make the life easier for the control side. So after we have a prototype, a proof of concept, or actually the final system, we do system identification to check the frequency response, to see if it matches with the model, if it has any modeled aspects, strange resonances, if there's bad assembly that shows some artifacts in the frequency response. So if we see this kind of stuff, we come back to the mechatronic design or even in the assembly itself of the system. If not, we go to design controllers, we implement them digitally, test the performance, and if the specification, and we test the specifications, if they are met. If not, we try to improve the controller, try different techniques, different tunings. And if it's not possible, we have to come back to the design. So it's basically a workflow to design the digital controllers for these mechatronic systems. And the first step, the mechatronic design, as I said, is a very multidisciplinary part. So it involves establishing specifications and modeling disturbances and trying to design the system, considering everything together. So we use lumped mass models, we use finite element methods to come up with the best model we can. And we use these models together with the models of the disturbances, so for vibrations, electronics, noises, cryo-coolers, vibrations, and we put everything together with a fixed control loop structure, which we try to optimize. Nowadays, we optimize more like the bandwidth of the controller to see which would be the optimal bandwidth based on this modeling. Of course, we can't just extend the bandwidth forever because we have limited actuators and we would amplify noise. But this is like the first step. We already take into consideration controls there. So after we have a physical system, we do system identification. For this type of systems, we are using a multi-sign excitation input. So a bunch of sinusoidal signals summoned up, and we control the phase of each component with a Schroeder phasing. It's a technique that reduces the crest factor of the signal, which is basically the ratio of the peak of the signal with the RMS. This is a way to minimize excitation of like non-linearities of the system. Internal modes, we want just to come up with a very linear model here. Okay, so we take several periods of this multi-sign signal. We do a windowing at the start and at the end to, again, smooth the response of the system, try to excite the less energetic modes and non-linearities as possible. And we use this, we implement this in a compact reel platform, which is the same that we will implement the controller later. We apply this excitation signal in each input of the signal, acquire all outputs simultaneously to get a minimal frequency response. So we have a frequency response relating all inputs with all outputs. We do that for many operation points to check how the dynamics vary there. So for example, we see that for a cryogenic and non-cryogenic operation of the system, these resonances move a little bit due to thermal expansion and stuff. We also estimate relative gain area, so we can be sure that there is some, what is the degree of decoupling between these degrees of freedom. So for this system, for example, we see a good decoupling up to 400 Hertz, which give us confidence to go to the loop at a time design, a decentralized control. And again, we validate this by iterating the test parameters here from the multi-assign excitation input. So okay, given a decoupled design, decoupled response, we are confident to work with a decentralized control. So nowadays we are working only with this, with CISO design. So when we do this system identification, we are already taking into account decoupling matrices. So we use decoupling matrices from sensors and actuators. They are basically homogeneous transformations from the position of the sensors and the actuators, coordinate systems to the coordinate systems of interest, for example, X, Y, and Z. We want to control that. So we already have the decoupled design. And with this, we move on to design the CISO controllers. So, well, we start with the loop gain definition, which is the transfer function of the combined controller, the plant, and the sensor dynamics. So it includes the phase of that. So we have this loop transfer function. From it, we can define also the closed loop transfer functions relating all inputs, the disturbances, the noises, the reference, to the signals of interest, which are the outputs, the error signal, the control effort. And when we come up with all of this, we see that there are some trade-off in the design. This is very classical for a control problem. So if you try to make the output track the reference well, you will not reject very well the disturbances. So we have a compromise there, and the solution is just to deal and to live with it by setting high gain at low frequencies and low gain at high frequencies. So the transition of these two parts is where the loop gain crosses the unity gain, which we'll define here as the bandwidth of the system. And this is a very classical setup. And now what we want to do is to make the loop gain have the shape that you want. So we use the loop shaping method. For this, we always, for these systems, we have been using a fixed PID-like structure. So it is composed by a proportional gain, one or two integrators, a lead compensator for phase margin, and some filters, so a low-pass filter to attenuate measurement noise, and also some high-frequency dynamics that will not, it's very outside of bandwidth of interest, and some notch filters to deal with resonances that are bad for the margins. And we also like to separate them in this second order blocks, so that when we discretize them, we provide a much higher numerical stability than if you discretize the entire transfer function at once. So we set some design specifications for the bandwidth. It comes generally from the first step during the design of the mechatronics that optimizes the bandwidth that we want to reach. It has been between 100 and 300 Hertz. We set a modulus margin of maximum 6 dB. The modulus margin is basically the peak of the sensitivity function, or how far you are from the critical point in the Nyquist plot. So this is like a more convenient way to define robustness than gain margin and phase margin. It's kind of a combined margin there. And to do this tuning, the loop shape tuning, we are doing currently manually using a MATLAB tool called ShapeIt. It was developed by the IACOW2025 and some researchers there. And it's pretty similar to CISO2, Control System Designer from MATLAB, but we like it a lot because it's very fast and it has a great advantage that it already exports the controller in these separate blocks. So I really recommend it. It's a free tool available online. And when we do this manual shape, we are looking at the different transfer functions. So the open loop, the sensitivity, and the Nyquist plots, we can move between them in this with the selectors. And okay, so this is what we are doing now. We are envisioning using more advanced techniques like H infinity, H2. I know there's a talk about it, so it will be interesting to see later. Okay, so feedback control can do everything. So some systems need to follow a trajectory. And if you want to follow a very well trajectory, we would need to open too much the bandwidth of the controller, but this causes problems for the measuring noise. So we do a reference feed forward. And when you do a reference feed forward here, you have the simplified here. We have this closed loop transfer function, in which we see that if you approximate f to fg to 1, this transfer function goes to 1, and the output matches the reference, which is what we want. So to do this, we can use the model inversion technique. So you just say that f is equal to the inverse of g. And of course, this is not ideally possible, practically possible, because if we invert, if you invert the dynamics of a physical system, you have a non-causal system there. So it's never possible to do this inversion, but you can use it in smart ways to have some results. So for example, for motions that require S-curves, so it's polynomial curves, we just provide all the derivative terms of the trajectory. We multiply them with gains. And we already provide like a non-causal transfer function for this feed forward. For this, we need a parametric model. We fit usually a second order model with our data. And we can come up with Kp, Kv, and Ka related to the velocity, positions, acceleration terms. Another technique we are exploring now is for periodic references. So we actually take the identified plant, invert the data we have to mount a lookup table. We embed this in the controller. And when we have this periodic references, for example, this almost square wave signal here, composed by many harmonics, we just provide the information about these harmonics, amplitude, frequency, and phase for the trajectory generator and for the feed forward. The feed forward will apply a gain and a phase for each of these components to generate a feed forward effort. It has worked well when the plant doesn't, the dynamics doesn't change much. So we have a work in progress to make an online estimation of this gain phase response as well. And the digital implementation, after we have come up with these controllers, we implement them in a compact real platform, which has a CPU and an FPGA core. Of course, the FPGA is dedicated for the control loop. The CPU is more for high-level stuff like file handling, epics, and stuff. And the implementation here has been in 20 kilohertz simple frequency. We discretize each block of the PID controller separately to improve numerical stability. Using testing discretization, we always will use pre-warping so that, for example, the center frequency of the notch filters doesn't move. The implementation in the FPGA is done in double precision floating point, 64 bits, so it makes easier the life of the developer, so we don't have to worry too much about the ranges of the fixed point implementation. And we need double precision for the dynamic range. So for example, we have stages that move millimeters with a precision of nanometers. So we need that kind of resolution. We have a custom transfer function solver developed. We have a work we'll present tomorrow here about it, which consists of a reconfigurable chain of impulse response filters in series that we can reconfigure online and have a lot of these chains, so we can control many degrees of freedom. Everything is done in LabVIEW. We reprogram this in LabVIEW. And of course, the system identification and acquisition functionalities work along with it for validation tests and for experimental usage as well. So just some applications we have been using this framework. So the double crystal monochromator, which selects the energy of the beam for the experiment by setting the angle of two crystals. So we have to set the angle of these two crystals with a goniometer, a brushless DC motor, and also control the distance, roll pitch between these crystals. And so we have achieved stability, a steady stability in these crystals better than 10 nanometers. So actually for the gap, which is the distance between the two crystals, we achieved a better than 1 nanometer stability. We have been able also to do fast scans. So we have an example here of a 10 hertz scan. One of our beamlines is using 5 hertz scans nowadays. So they are able to measure an absorption spectrum at 5 hertz. As we measure in both directions, we have like 10 spectrums per second. This is another application. It's a cryogenic sample stage Sapoti for the Carnaúba beamline, which is a sample stage to position. Is a stage to position the sample. It has a 3 millimeter sphere working volume, and our stability spec is 1 nanometer. We are still working to reach them, but we already have for a non-cryogenic operation better than 4 nanometer. We can also do fast fly scan operation. And finally, an application that it's working in progress. It's a quarter wave plate for circular dichroism experiments. So basically, we have a crystal here where we want to polarize circularly and linearly by changing the angle of the crystal. And in one of the operation modes, we need to do that in a locking operation, so it will change the polarization while measuring the instrumentation with a locking amplifier. And the goal is to work with 100 hertz frequency, and we have seen good results. This is where we are using this method of feed forward. So we have some references here, and that's it. Thank you.